Have you ever wondered how digital data can be sent from one device to another? One of the simplest ways is the UART protocol, which we'll explore using Arduino today. Today we are exploring how digital data moves between chips using the UART protocol. UART stands for Universal Asynchronous Receiver Transmitter. But don't worry about the fancy name. On Arduino, we simply call it serial interface, because data is sent one bit at a time. This simplicity is what makes it brilliant. It requires only one wire per direction. Compare this to parallel communication, where you need multiple wires to send multiple bits at the same time. So how is it possible to send data on a wire? Well, first we need to define some rules for both transmitter and receiver to allow data to flow. Think of it like a language. If I suddenly speak German instead of English, dann können mir die meisten von euch nicht mehr folgen. Just like we agreed to use English for this video, UART needs its own set of rules. For Arduino, one of the most important rules is the baud rate. That's how many bits per second we're sending. Now here's something interesting. Even if we set it to 9600 bits per second, we'll never actually reach that number. Why? Let me show you with my logic analyzer. We need to connect ground, of course. And then we need two wires, because we have two directions, RX and TX. The receive pin and the transmit pin. Arduino UNO has the receive pin on pin 0 and the transmit pin on pin 1. This is the hardware UART interface. You can also use soft serial. That way you can define different pins as transmit and receive pins. But in the end, it's a lot of work for our poor Arduino. Keep that in mind. So the first example, I will start with a baud rate of 9600 and I will send the character A every second. Let's upload the sketch. On the logic analyzer, I can see that every second we get something on one of the lines. Right now, Arduino is sending data every second. It's only a data flow in one direction because Arduino sends out data and no one replies. If I zoom in, then we can see something like this. Now this is one data transmission, and the data transmission starts with a start bit. Then it continues with 8 bits, which is 1 byte. It starts with the least significant bit and it ends with the most significant bit. And the transmission itself ends with a stop bit. Now if we measure one bit is transmitted with a duration of 104 microseconds. And if we do the math, that is approximately 9600 bits per second in theory. But the problem is that we have the start bit and we have the stop bit. Let me show you what happens if we actually send multiple characters. So let's send A, B, C. And now we can see with a start bit, we have 8 bits, we have a stop bit, we have a start bit, we have 8 bits, we have a stop bit, we have a start bit, we have 8 bits, and we have a stop bit. So this is why we will never reach this 9600 bits per second in terms of data bits. We also have the start bit and the stop bit, and they also take some time. So in practice, when it comes to actual data transmitted, we can reach about 80% of this 9600 bits per second. You might be thinking, why do we have to start and stop this transmission every 8 bits? That makes no sense, right? We could just continue to send data. Why not? Well, because the transmission is asynchronous. We need the start and stop bits to sync the sender and the receiver. Because after 8 bits, they expect this transition. Basically, it comes down to the accuracy of the crystals. Two Arduinos are not working with exactly the same frequency. And that's why these deviations will lead to deviations in this data transmission. And then eventually we interpret a bit wrong. And that's why it's limited to 8 bits. So the most important rule is the baud rate. If we increase this baud rate here to 19,200, for example. These are actually 3 characters and the receiver thinks it's 1.5. So in this case I have to edit and set the baud rate to 19,200. And then suddenly it works again. The baud rate is the most important thing, but you can actually do 3 more things. So the first thing is you can change the amount of data bits. The second thing is you can add a parity bit. And the third thing is you can change the amount of stop bits. Let's take a look. You can add another parameter right here. And on the Arduino website you can see that the default parameter is this one, and it basically represents 8 data bits, no parity bit, and 1 stop bit. And we can now change the data bits, for example, to 7. The newest captcha gives us some errors because, it's confused now, because we need to change the bits per transfer to 7. And now suddenly it works again. Now the funny thing is that we don't lose data because ASCII only requires 7 bits. So if we go to the ASCII representation of this data here, it shows A, B and C. We would lose 1 bit, but ASCII doesn't require 8 bits. It just requires 7 bits. However, if we reduce the bits to 6 bits, see some errors again. We need to change it to 6 bits. And now you see it doesn't make any sense. Now it's completely different characters because now we lose data. It's not possible to send ASCII using 6 bits. So we need at least 7 here, but I will go back to 8 and show you something else. And that is the parity bit. Right now we're using no parity bit. We can use an even parity bit or an odd parity bit. So let's use an even parity bit. That was to be expected because now we have an additional parity bit. So we have 8 bits and we have an even parity bit. Then we can see A, B, C again. The even parity bit ensures that the total number of ones, including the parity bit, is an even number. And if we look at this, we have 1, 2, 3, 4. And 4 is an even number. And in this case, we also have 1, 2, 3, 4. And in this case, we have 1, 2, 3, 4. Also an even number. This can be used to detect errors. Sometimes it's used in combination with ASCII, because ASCII only requires 7 bits and that leaves 1 last bit for the whole byte. And everything usually works with bytes, and so you could use this 1 missing bit as parity bit. And then the last thing that we can decide is the stop bits. So if we increase the stop bits to 2, and there's really only 2 options, you can have 1 stop bit or 2. So if we use 2, it just increases the time between 2 transmissions. I would like to conclude this video with an example where I use 2 Arduinos. This Arduino UNO R2 will be connected to a potentiometer, and this Arduino UNO R3 will be connected to an LED. So this Arduino sends this value to this Arduino, and this Arduino then sets the brightness of the LED accordingly. First, let's connect all of the ground connections. Go around. All of these contacts here are connected to ground. The Viper to output the signal to A0, and I also need 5 volt. So like this, I should be able to measure analog voltage. Let's connect pin 10 to the green LED using a resistor. Don't use your Arduino UNO R4 for this. If you don't know why, watch my video about Arduino R4. We need serial begin. Let's stick to a baud rate of 9600. Unsigned int analog value equals analog read A0. So let's do it like this, and then we need to talk about it. As you can see, this value starts at 0 and goes up to 1023. That's the maximum number because it's a 10-bit analog digital converter. If we send it like this, we need up to 5 bytes to transmit this data. So I would like to actually do two things. The first thing is our second Arduino will generate a pulse width modulated signal, and that only has a resolution of 8 bits. So from 0 to 255. So the first thing is I will reduce the 10 bits to 8 bits. And I can use map for this. So I can map this value from 0 to 1023. And it should be from 0 to 255. So now it's mapped down. That's the first step. And the second step is I would like to send it as a number. So let's use serial write. And if we do that, we can't read anything anymore because it's not ASCII anymore. But that's fine, hopefully. We don't know yet. Let's go to the other one. On this Arduino, we just need to receive this data and then set the pulse width modulation of the LED accordingly. So first, serial begin 9600. It's important to use the same baud rate. Inside of our loop, we will check if serial data is available. So if serial data is available, then analog write pin 10 to serial.read. Right now they are not connected, so I can rotate the potentiometer, nothing happens. As soon as I connect them, and now I need to think, here we need to transmit, and here we need to receive. As soon as we connect them, you can see that I can change the brightness. There's one last thing that I would like to change, because right now we're sending a ton of data. So this Arduino right here is sending data as fast as possible, even if the value doesn't change. This one cable sees a lot of traffic, but it doesn't really matter as long as we don't do other things. But it would make sense to only send data if the value changes. We need to save the old data and compare it to the new. After measuring the analog value, we need to check if analog value is different from old analog value, which we don't have yet. If it's different, then you can send the data, and you can also, or you have to, assign the new value to the old value. What is this old analog value? Well, we need to define an unsigned integer old value. Let's start with 0. You can see the difference on the transmit LED here, because if I change the value, it continuously sends, and as soon as I stop rotating, it doesn't send anymore. Only if the value changes, then it sends data. And if it doesn't change, it doesn't send any data. That's exactly what we want. If it's exactly in between two values, then it will continue to send data. If this video was helpful, please like and subscribe to this channel if you're ready to dive deep into the world of Arduino. And if you would like to know why you shouldn't use Arduino UNO R4 for this setup, check out this video here. Thank you for watching. See you in the next video.